Hello everyone, welcome to IKSR chemistry classes. In this video, we are going to discuss the most burning issue which is joggling our mind these days, and it is nothing but the role of boron to prevent the nuclear radiation leakage. We will start our discussion from very basic to advanced level. First of all, let us see what is atom and what are its constituent particles. The smallest unit of an element having all its properties is called an atom. Atom consists of three fundamental particles: positively charged protons, neutral neutrons, and negatively charged electrons. Proton and neutron are present at the center of atom, which is called nucleus. On the other hand, the negatively charged electrons revolve around the positively charged nucleus in the extranuclear region. Now, what is nuclear fission? Fission means dissociation, breaking up. When a large nucleus splits up into two smaller nuclei with comparable masses, the phenomenon is known as nuclear fission. The large nucleus which undergoes nuclear fission is called fissile nucleus. On the other hand, the small nuclei produced as a result of nuclear fission are called fission products. What happens in the fissile nucleus? What is the feature of a nucleus that it is fissile? It is nucleus consisting of positively charged protons and neutral neutrons. There is overall positive charge on the nucleus. In the nucleus, two types of forces act mainly. The first one is repulsive electrostatic force. It acts between positively charged protons. The other one is attractive exchange force. It acts between proton-proton, proton-neutron, or neutron-proton, and the attractive force, this one, that is exchange force, is of same magnitude in all the three pairs I have said: proton-proton, neutron-proton, and neutron-neutron. It must be noted that the electrostatic repulsive force is a long-range force. It can act up to a long distance, but the exchange force is a short range force and it acts up to a short distance. For a medium sized nucleus, the attractive force is about 100 times stronger than the repulsive force, and this is why most of the small and medium sized nuclei are stable. But as the size of nucleus increases, the attractive exchange force decreases rapidly because it is short range force. But the repulsive electrostatic force decreases slowly because it is a long range force, and a situation comes when the attractive force becomes approximately equal to the repulsive force. And this type of delicate balance between attractive and repulsive forces in the nucleus makes it fissile. Even a small disturbance can lead to its fission. Let this nucleus, having delicate balance between attractive and repulsive forces, is bombarded by a neutron. This delicate balance is disturbed, is destroyed by the kinetic energy of incoming neutron, and this nucleus splits up into two smaller nuclei, and during this process 2, 3 or 4 extra neutrons are also ejected. Thus, in the fissile nucleus, there is a delicate balance between attractive and repulsive forces. Two common examples of fissile nuclei are U-235 and plutonium-239. These two are the most common example of fissile nuclei. A specific example of nuclear fission is given below. When the nucleus of U-235, having a delicate balance between attractive and repulsive forces, is bombarded by neutron, a compound nucleus is formed by the capture of neutron by this nucleus. And the delicate balance between attractive and repulsive forces is destroyed in the compound nucleus, and it splits up into two smaller nuclei with comparable masses. 3 neutrons are ejected here, which may be 2, 3 or 4, and some energy is released. These products, the fission products and ejected neutrons, have mass about 0.22 AMU less than the mass of compound nucleus, and this loss in mass, that is 0.22 AMU, is converted into energy, and this energy becomes equal to 0.22 multiplied by 931.5 mega electron volt, and it is equal to 205 mega electron volt. This energy may be different depending upon the nature of fissile products and the number of neutrons ejected. Here, uranium-235 is target nucleus. The neutron by which we have bombarded this nucleus is called projectile neutron. It is compound nucleus. These are fission products. It is ejectile neutron. And this is a specific example of nuclear fission. The neutrons ejected in this way, these neutrons which are ejected during nuclear fission, can cause the fission of other nuclei of U-235, and thus a chain reaction of nuclear fission may be established. And it can be represented diagrammatically as follows. It is target nucleus which has been bombarded by neutron. As a result, this neutron is captured by the target nucleus, forming the compound nucleus, and then the compound nucleus splits up into two smaller nuclei with comparable masses, and here 3 neutrons are also ejected during this nuclear fission. And now, types of chain reaction of nuclear fission. The chain reaction of nuclear fission is of two types. The first one is non-controlled chain reaction. The chain reaction of nuclear fission, in which the number of U-235 nuclei undergoing fission per second goes on increasing rapidly, is called a non-controlled chain reaction of nuclear fission. And it has been represented diagrammatically here. This is U-235 nucleus which is being bombarded by the neutron. This nucleus splits up into 2 fission products, and 3 neutrons are being ejected during this process. These 3 neutrons will cause the fission of other 3 nuclei of U-235, and as a result 9 neutrons will be ejected. Let us see at a starting, that is time equals to 0, 1 nucleus of U-235 undergoes fission producing 3 neutrons. After 1 second, 3 nuclei of U-235 will undergo nuclear fission. After 1 second, 3 nuclei of U-235 undergo fission, and after fission of 3 nuclei, overall 9 neutrons will be ejected, and at the end of 2 seconds, 9 nuclei of U-235 will undergo nuclear fission, and at time 3 seconds, 27 nuclei of uranium-235 will undergo nuclear fission. And imagine what about in 60 seconds, the number will be 3 to the power 60. And on adding all these numbers, we get 10 to the power 29. It means 10 to the power 29 nuclei of U-235 will undergo nuclear fission, and accordingly a large amount, an enormous amount of energy will be released, and such a situation will be called nuclear explosion. And therefore atom bomb is based on non-controlled chain reaction of nuclear fission. And the second one is controlled chain reaction. The chain reaction of nuclear fission, in which the number of U-235 nuclei undergoing fission per second remains almost constant, is called a controlled chain reaction of nuclear fission, and it has been explained, illustrated diagrammatically as follows. One U-235 nucleus is bombarded by a neutron, and it undergoes nuclear fission, producing fission products and 3 neutrons, out of which 2 neutrons are absorbed by applying neutron absorber, and only 1 neutron proceeds further to cause the nuclear fission of other nucleus of U-235. And this situation is repeated further. That is, every time 1 nucleus of U-235 undergoes nuclear fission, and as a result, energy is released in controlled way during controlled chain reaction of nuclear fission, and this energy can be transformed into useful form such as electrical energy, and therefore nuclear reactors are based on controlled chain reaction of nuclear fission. And now let us see the energy released during nuclear fission is shared between or among which type of particles. This is the total energy released during nuclear fission, which may be 205 mega electron volt or somewhat different. The major portion of this energy is shared by the fission products. The major amount of energy released during nuclear fission appears in the form of kinetic energy of fission products, and about 80%. This amount is about 80%. 80% of the total energy appears in the form of kinetic energy of fission products, and about 15% is shared by neutrons, gamma rays, neutrino, antineutrino, etc. And the kinetic energy of fission product is ultimately transformed into heat energy due to collision with atoms or molecules in the surroundings, and this heat energy can be transformed into other useful form. And now, what is the harmful effect of neutron radiation? Neutron radiation is ionizing in nature. It can penetrate into our body due to its small size is very small, and higher velocity. It causes damage to DNA. The DNA present in the nucleus of our cell is damaged by neutron, and it leads to cell mutation causing cancer, because the cell mutation of cancerous cell leads to uncontrolled growth of cells, and the uncontrolled growth of cells appears in the form of tumor. In other words, we can say that neutron radiation causes cancer to human beings, which is very dangerous. And neutron radiation is even more effective than X-rays and gamma rays in causing cancer. Let us illustrate the growth of tumor by neutron radiation by diagram. This is a cell present in our body, and it is the nucleus of cell which is irradiated by neutron. As a result, the DNA, the sequence of amino acids in the DNA is disturbed. That is, DNA is damaged, and this cell becomes cancerous, and its mutation leads to formation of a number of cancerous cells, and which appear in the form of tumor. Thus, neutron radiation can cause cancer in human beings. And now the main topic, boron, which is an element discussed much today. Boron is a dark colored lustrous crystalline metalloid with atomic number 5. This is boron, dark color lustrous crystalline metalloid, whose atomic number is 5, and it occurs in the form of two isotopes. One isotope is B10, whose mass number is 10, then the other one is B11, whose mass number is 11. Both these isotopes of boron have 5 protons, 5 electrons, but B10 contains 5 neutrons in the nucleus, while B11 contains 6 neutrons in the nucleus. It must be noted that natural boron contains 20% B10 isotope and 80% B11 isotope. It means B11 is more stable than B10. Natural boron consists of two isotopes, B10 and B11. B10 is less stable while B11 is more stable, and therefore B10 isotope of boron has a tendency to be transformed into more stable B11 isotope by absorbing neutron. This is B10 isotope of boron, which absorbs one neutron and it transforms into more stable B11 isotope. Thus, we can say that boron 10 has ability to absorb neutron. Nucleus cross section of B10 for neutron capture. Neutron capturing nuclear cross section of B10 is 3840 Warn. For neutrons having lower energy than 0.025 electron volt, that is for thermal neutrons and slow moving neutrons. For thermal or slow moving neutrons, the nuclear cross section of B10 isotope of boron is 3840 Warn. Now the question arises, what is Warn? Warn is the unit of area, and it is equal to 10 to the power minus 24 centimeter square. And this Warn is abbreviated as a small b. the actual radius of B10 nucleus is 3 into 10 to the power minus 13 centimeter. This is the actual radius of B10 nucleus. But the effective radius of B10 nucleus has been calculated to be 3.5 into 10 to the power minus 11 centimeter. This is effective radius of B10 nucleus. And this one is about 100 times of the actual B10 nucleus radius. Nuclear cross-section of some nuclei for neutron capture are given in the following table. B10 has nuclear cross-section in Boron 3840. On the other hand, B11, which is a stable one, has very small nuclear cross-section to absorb neutron. On the other hand, U235 has high 584 Boron nuclear cross-section for capturing thermal neutrons, while uranium-238 has very little nuclear cross-section for neutron capture. Plutonium-239, which is also a fissile nucleus, has high nuclear cross-section. It must be noted that higher the value of nuclear cross-section B in unit B for capturing thermal neutrons, higher will be its ability to absorb neutrons. This is why B10 isotope of boron has very high ability to capture neutrons. And it can be represented diagrammatically as follows. This is B10 nucleus. It has been divided into two equal parts. Then we get two such hemispheres with radius r, which is actual one, and its cross-sectional area is represented by this one. This cross-sectional area, actual nuclear cross-section, which will be equal to pi r square, and actual nuclear cross-sectional area of B10 nucleus is 0.283 Boron. But the situation is different. In actual practice, the effective radius of B10 nucleus for capturing neutron is about 100 R, 100 times greater than the actual radius, and the effective cross-sectional area is 3840 Boron. Let us illustrate it with the help of a two-dimensional figure. It is the actual nucleus of B10, and this one is the effective. The actual radius of B10 nucleus is 3 into 10 to the power minus 13 centimeter, while the effective radius is 3.5 into 10 to the power minus 11 centimeter. Let a neutron travels in this direction. Neutron is traveling in this direction, a small neutron. This neutron is not expected to be captured by this nucleus because its path is away from the nucleus. But according to de Broglie theory, any small particle moving at high velocity is associated with a wave which is called matter wave. It means the neutron will not move on a straight line, its motion will be like a wave. And on this point, this neutron will be absorbed by the nucleus. In other words, we can say that any neutron passing through this effective area will be captured by the nucleus of B10, and this is why B10 has very high ability to capture or absorb neutrons. And let us see conclusion. But if you are still watching the video, you have liked it, and please therefore have a like for the video. Boron is the most effective material to absorb the neutron radiation emitted during nuclear fission. The most effective material is boron to absorb the neutron radiation released during nuclear fission, and it subsides the harmful effects caused by leakage of neutron radiation. Thank you for watching the video. If you have any comment, please put it down, and if you like the video, you can share it to your friends, and if you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.